Hello everyone, I'm Junming from the Tunji University, and the topic of my report today is the process-dependent modeling for 3D printing continuous fiber reinforced composites. And my supervisor is Professor Li and Professor Weidong. And my report is divided into the four parts, and the first one is the background. And as is well known, the continuous fiber reinforced composites, as short as the CFRCs, has been widely used in the fields such as aerospace, vehicles, and ships at all. And compared with the traditional composite manufacturing method, the 3D printing has advantages such as better production without mold, low cost, and high manufacturing flexibility at all. However, there are still many meso and micro scale defects in the 3D printed CFRCs, which make their mechanical properties significantly reduced. Thus, it is very important to clarify the mechanism of the defect formation process, and thus we can optimize the printing parameters to reduce the manufacturing defects. And the temperature variation of the materials during the 3D printing process is shown in this figure, and it can be seen since that the material is directly exposed to the environment. The rapid heat dissipation makes the materials cooling rapidly, and the rapid cooling of the resin leads to insufficient impregnation within the fiber bundles, resulting in interbundle defects. It also causes insufficient interlayer bonding, which leads to delamination in the 3D printed CFRC parts. And many researchers have improved the thermal field during the CFRC 3D printings, and it can be seen that the interlaminar strengths have been significantly enhanced, and their macro CT and SEM results show that the improvement of thermal field further reduced the void content in the 3D printed CFRCs. Thus, it's very important to clarify the thermal history information of the materials for understanding the defect formation process. And in the current studies, the thermal field modeling is mostly focused on the pure resin materials, leaking models for the CFRC printing process, and there is little model for defect formation process in the CFRC 3D printing process. So it is impossible to predict the mechanical properties of 3D printing CFRCs directly according to the printing parameters. Considering this knowledge gap, the object of our study is to establish a simulation framework of thermal field and the defect formation process. Thus, we can optimize the printing parameters and manufacturing CFRCs with low defects and high mechanical properties. And the second part is the modeling. We first model the heat transfer behaviors during the 3D printing process, and from the IR images and our previous research, the following assumptions are proposed to simplify the heat transfer governing quotient into a zero-dimensional problem. And the 6 kinds of heat transfer boundaries are divided into 4 main types in the thermal field modeling, and the corresponding volume heat source are calculated. And then the governing quotient of the heat transfer is solved discretely for the subsequent numerical simulations. After completing the thermal field modeling, the impregnation process is studied. And we model the impregnation process based on the Darcy's law, and the polar coordinate system is used to calculate the impregnation distance along the pressure directions. And the equal proportion method is to calculate the impregnation distance perpendicular to the pressure directions. And the geometric parameters of the fiber bundles, which determine the permeability and the viscosity of the resins, are determined by the experiments I mentioned in the following the part 3. And the bonding process in the 3D printing is shown in the left figure. We can see that the material is deposited from the nozzle, and the material is gradually deformed under the printing pressure. and then the material bound to the previous layer. We first model the intimate contact occurred between the two layers under the pressure, and the intimate contact model is modeled based on the thermoplastic modeling model proposed by Lee and Springer. And the single filament section is simplified to a rectangle to calculate the intimate contact degree. And intimate contact degree will further affect the heat transfer boundaries and then change the thermohistory information of the materials and then change the diffusion degrees. So it is necessary to carry out the heat transfer boundaries aerations in the heat transfer simulations and bonding simulations. And then the diffusion process is occurred in the interface formed by the intimate contact, and the diffusion degree is calculated by these equations. And finally, the bonding strength is determined by the intimate contact degree and diffusion degree jointly. And finally, we built a multiscale analysis model to calculate the axial tensile strength and the transverse tensile strength. In the microscale, we established the RE model considering the fiber and resin distributions. And in the mesoscale, the void in the interbundles is further considered. The void the distribution and the content of the void is calculated by the impregnation models. And in the axial tensile strength, the macroscale model is directly simulated by the results result of the mesoscale. And in the transverse tensile strength, the cohesive element is further established between the two layers according to the simulation result of the bonding strength models. And then the macroscale simulation model is calculated to calculate the transverse tensile strength. And the third part is the validation. And we designed the corresponding experiments to validate the models we proposed. First, we built the prepreg filament preparation equipment and the 3D printing equipment to manufacturing the tensile spacemans. And the mechanical and thermal properties of the PLA and carbon fiber we used in the experiment is shown in the right table. And in the thermal field model validations, we first designed the experiments to determine the key heat transfer parameters in the thermal field model. And then we used this model in the thermal field simulations and validated against the experimental result. From these figures, we can see that the simulation result is in a good agreement with the experimental results. And then we simulated the whole printing process used by the thermal field models. And the thermal history information of the material is recorded by the thermocouples in the experiment. Based on the measured heat transfer parameters, the established thermal field model can achieve a current predictions of the thermal field during the printing process. And from the left figures, we can see that the thermal field models captured the three temperature peaks found by the material deposition, the material heated by the nozzle, the materials heated by the laser successfully. And then we measuring the printing pressure during the printing. From these equations, we can see that both in the impregnation and the bonding behaviors, pressure is a critical parameters. Thus, we built a printing pressure measurement platform based on the force sensor and measured multi-layer pressure in the printing. And the printing pressure's result is shown in the following figures. We can see that the printing pressure decreases rapidly with the decrease of the layer height. And when the layer height approaches the diameter of the prepreg filament is about 0.55 millimeters, the pressure approaches to zero. And after the mechanical test, the corresponding tensile specimen is prepared as the metallographic specimen to be observed under the optical microscope. An in-house MATLAB program is used to segment the metallographic specimen images based on the grayscale values to determine the impregnation degree. And the image segmentation and boundary extraction were performed on the metallographic specimen images to determine the intimate contact degree. And next is the impregnation and the intimate contact degrees validation. And the impregnation process is mostly affected by the thermal field. So we verify the thermal field by adjusting the laser powers. And the intimate contact process is more sensitive about the printing pressure. So we verify the printing pressures by adjusting the lead height. And from this figure, we can see that the predicted impregnation and intimate contact results are in good agreement with the experimental measurements. And the maximum error in the predicted results is below 5% in the impregnation, while that of the intimate contact remains below 10%. And the experimental and simulation results related to the axial tensile strength are is shown in this figure. We can see that the simulation results are also in good agreement with the experimental results. The impregnation degree of the sample can be significantly improved by regulating the thermal field with the laser assistance, thereby enabling secondary impregnation process. And the impregnation has a significant impact on the axial tensile strength. And we can see that a high impregnation degree will cause a decrease in defects within the fiber bundles and increase the axial tensile strength. And the transverse tensile strength validation is shown in the left figure, and the failure mode prediction is shown in the right figure. We can see both the transverse tensile strength prediction and the failure mode prediction are in good agreement with the experimental results. The increase in printing pressure leads to an increase in the intimate contact and the diffusion degree, resulting in an increase in the bonding strength. And as the interlayer bonding strength improves, the dominant failure mode shifts to damage induced by interbundle voids. Consequently, insufficient interbundle strength becomes the primary factor limiting the transverse tensile strength. And the final part is the conclusions. From the above experiment, we can have the following conclusions. The established thermal field impregnation, intimate, and axial transverse tensile strength prediction models can all achieve prediction errors of less than 15%. And the thermal field improved can significantly enhance the impregnation degree of the 3D printed CFRCs and improves their mechanical properties. And specifically, it can increase the impregnation degree by more than 10% and the axial tensile strength by over 30%. Increasing the printing pressure can enhance interlayer bonding by reducing the interlayer void content and promoting the diffusion process, resulting in a 400% increase in the transverse tensile strength. And this is the end of my report. Thank you for your attention.